Hello and welcome back to our next lecture. In chapter 6, we're going to pick up where we left off, which was we had just been going over electron configurations. And since the periodic table was originally set up by grouping together atoms that had similar properties, it turns out that the reason they have similar properties is because they have similar electron configurations. And that means that the periodic table is set up according to electron configuration also. And since, because of that, and because various properties will vary according to the electron configuration, that means there are various properties of the elements that vary according to where they are in the periodic table. And having an idea of what these trends and what are known as periodic properties, knowing what those trends are like, can help us to be familiar with what elements are like just by where they are in the periodic table. You don't really have to have any personal familiarity with that particular element. And as I said, said before, when we were talking about the periodic table, when Mendeleev was setting up the periodic table, he was grouping the elements together according to their elements with similar properties. He was grouping together, and there were several holes in his periodic table where elements that just hadn't been discovered yet would later, fit. And he predicted not only that those elements would eventually be discovered, but he predicted with pretty good accuracy what their properties would be like too, just based on where the vacancies in his periodic table were located. So again, you can tell a lot about an element just by where it is in the periodic table. And the things that he was predicting were what are now known as periodic properties. They vary regularly within the periodic table, and since they vary regularly, they are predictable. And so you can, like I said, you can know a lot about an element just by where it is in the periodic table. Since electrons configurations repeat periodically and many properties depend on electron configurations, the properties themselves will also repeat periodically and predictably throughout the periodic table. And that leads to predictable trends for many interesting properties. Some of the properties, and these are not all of the periodic properties by any means, but the ones that we're going to discuss in the rest of this chapter will be ones like metallic character. That is, to what degree does an element do the kinds of things that metals like to do, like losing electrons to become cations, that kind of thing. The size of the atoms or the radius of the atom, which since we tend to envision atoms as spheres, more or less, the radius would just be the distance from the nucleus to the outermost limits of the valence shell. But radius is what we usually use as a stand-in for size of the atoms. The ionization energies, that is, how much energy do you have to put in to get an electron away from an atom? That varies according to where the elements are in the periodic table. And electron affinities, which is kind of the opposite of ionization energy. The electron affinity is how much energy is released when an atom takes in an additional electron. Related to that is the property of electronegativity, which I've mentioned before. The electronegativity is the attraction that an atom has for electrons within a bond. Electron affinity is basically the attraction that an atom has for electrons when it's a free atom, but electronegativities are the attraction that an atom has for electrons when it's involved in a bond. And they're not exactly the same thing, although they are related to each other. We'll go into electronegativities in a lot more detail in the next chapter. So there's something to look forward to. For metallic character, as I mentioned briefly above, a metallic character can be considered to be the degree to which an element does the things that metals like to do. And some of the things that metals like to do, the most important one for a metallic character is metals like to lose valence electrons to form cations. Okay. But also metals conduct electricity and they're malleable. That is, you can hammer them into a flat sheet without having them shatter and break apart. And those are all things that metals like to do. And So metallic character is basically the degree to which an element exhibits these characteristics. Generally, the metallic character, oh, I've got these exactly backwards for some reason. Metallic character increases toward the left and going down a group. And I'm going to pause here while I fix this, and I'll be right back. Okay, back and fixed. That looks a little better now. I don't know how I got it backwards like that, but anyway, the metallic character increases going to the left and going down. And I found when I was trying to remember the trends in periodic properties when I was a student, that the easiest way I had of remembering them was just to draw little arrows like this, indicating the direction on the periodic table in which the properties increases. Because in the textbook they will explain, oh, it increases this way, but it decreases going that way. And trying to remember all of that stuff, increases to the right, decreases to the left or down, and it can get very confusing. And so I tended to draw a little diagram, and I just sort of remember the diagram for each property. And to be consistent, I always draw the arrows in the direction in which the property increases. So metallic character increases to the left and down, and because that's where the metals are. They're to the left on the periodic table, and they're down. It's even over here where we have the non-metals on top, we've got metals down at the bottom. So metallic character increases going down, and it increases going to the left. The most metallic element of all would be cesium and francium. They're more or less equal, way down here in the lower left-hand corner of the periodic table. And the least metallic of all would be fluorine, way up in the upper right-hand corner. And that's essentially because cesium and francium lose electrons very easily, and they're also very soft, so they conduct electricity really well. They are very easy to hammer into a flat sheet. Just make sure that if you try doing that, make sure that there's no moisture on the hammer, because they react very violently with moisture, even the moisture in the air, actually. Fluorine does not want to give up electrons under any circumstances, and it is a really bad conductor of electricity, and it's a gas, so good luck trying to hammer it flat. It's not going to sit still for that. So yeah, so to the left and down would be the increase in metallic character. There may be cases where you have to judge an element based on its metallic character. Like, for instance, if you're writing the formula for a compound, especially if it's like one of the covalently bonded compounds that feature nothing but nonmetals, the convention is to write the formula with the more metallic element first. Well, if you're dealing with nonmetals, how do you do that? Because they're nonmetals, there are no metals. Well, there's metallic character. Whichever one is more metallic would be whichever one is further left and whichever one is further down. So, for instance, phosphorus is more metallic than oxygen because it's down and to the left. And so, that way you can know which order to put the elements in if you're trying to come up with a molecular formula. Also, size of atoms. Covalent radius, as I said, is what we use as a stand-in for size. This is basically, it's a way to define the size of an atom with a minimum of quantum mechanical uncertainty, because trying to measure the size of an atom from the center of the nucleus to the outermost reaches of the valence shell of electrons can be very difficult because of Heisenberg's uncertainty principle. We don't really know where those valence electrons are at any given moment. We can map out statistically where they're most likely to be at any given moment, but that's kind of fuzzy because there's no one distance that they're most likely to be from the nucleus. I mean, you could actually say, okay, the greatest likelihood for the valence electrons is to be this distance from the nucleus, but then there's an almost equal likelihood that they'll be a little further away or a little closer. And it's just that the probability gets lower and lower as you move further away from that spot one way or the other. But trying to say, that they're going to be at this distance is something that you can't really say with total accuracy. So the covalent radius is used. And what the covalent radius is half the distance between the nuclei of two atoms of the same element when they're connected by a covalent bond. So if you have, say, a hydrogen atom connected by a covalent bond to another hydrogen atom, you'd have a nucleus with a shell of electrons around it, and then you'd have another nucleus with another shell of electrons around it, and the distance between the nuclei in that bond, half of it would be considered the covalent radius for each of those hydrogen atoms. And it may not, and that may be somewhat different. In fact, it certainly is somewhat different from what we would think of as the distance from the center of the nucleus to the outermost electrons, because atoms come closer together when they form bonds. But this property is at least proportional to what would be the distance between the nucleus and the outermost electrons for an isolated separate atom. So we use this as kind of a convenient stand-in because this is something that we can measure accurately. The distance between the center of the nucleus and the outermost electrons is something that we actually cannot measure accurately. This property, covalent radius, increases like metallic character to the left and down a group. Now, having the size of atoms, or the covalent radius, increasing going down a group makes sense, because if you're going down a group, like say group 1 with the alkali metals, from lithium to sodium, you're adding a new shell of electrons. The outermost shell is shell number 2 for lithium, but for sodium, it's shell number 3. For potassium, it's shell number 4. You're adding a whole new shell of electrons for each step down a group. So it makes perfect sense that the atoms would get bigger going down a group, and they do. What may not make sense is the fact that atoms actually get better or bigger going backwards, that is, toward the left in the periodic table. Now, if you think about what happens, it still doesn't really make sense at first glance, because as you're going from left to right across the periodic table, for each step left to right, you're adding one electron to the valence shell and one proton to the nucleus. And so you might think, well, you're adding stuff to the atom, so it must get bigger, right? But keep in mind that the atom consists mostly of empty space. The actual protons and actual electrons in an atom are really, really tiny compared to the empty space between the nucleus and the electrons, and between one shell of electrons and the next. And what you're doing, each time you add a proton to the nucleus, the charge of the nucleus goes up by 1. So the nucleus is getting more and more positive as you go left to right. When you add one more electron to the valence shell is getting more and more negative. So the negative charge in the valence shell is getting bigger and bigger as you go left to right. And that bigger positive charge in the nucleus and that bigger negative charge in the outer shell of electrons ends up in a stronger attraction between the two, and they move closer. And they can do that because there's so much empty space between the electrons and other electrons, and between the electrons in the nucleus, that they're just really compressing empty space. It's really easy to do. And so higher nuclear charge and bigger negative charge in the valence shell is what makes atoms smaller as you go left to right. So if you want the direction in which the size increases, that would be toward the left. Okay, so covalent radius increases toward the left and down a group. And up here at the top is just written out what I just explained. Covalent radius increases down a group because you're adding a whole new shell of electrons each step down you take. But it decreases left to right, or in other words, it increases right to left, because each step left to right, you're adding a proton, which increases the nuclear charge by 1, makes it more positive, and you're adding an electron, which makes the charge on the valence shell more negative. And that makes them more strongly attracted. So they move closer, and they can do that because there's nothing but empty space between them. And so the atom becomes smaller as you're going left to right. Okay, across the transition elements, the charge or the change in radius for atoms is not as pronounced as it is in the A groups, but there is a change. And there is a way to measure the attraction between the nucleus and the outermost electrons, and that's called the effective nuclear charge. We're interested in the effective nuclear charge because especially in larger atoms, not all of the nuclear charge necessarily reaches the outermost electrons. So the degree of attraction between the outer shell electrons and the nucleus can be partially blocked by electrons in the inner shells of the atom. That is, any electrons that come between the valence shell and the nucleus will partially shield the valence shell from the nuclear charge. So they're basically shielding by inner shell electrons. The effective nuclear charge is given in the book as Z, the atomic number, which is the number of protons in the nucleus, and which is the charge, the positive charge on the nucleus. If you've got 3 protons in the nucleus, then the nuclear charge is 3, plus 3. So atomic number minus the shielding. They don't really go on to explain what shielding means. What shielding means, if you're talking about a valence electron, is the number of core electrons. So Z minus the number of core electrons. And the core electrons are just any electrons that are not in the valence shell. So core electrons would just be, well, Z minus the number of valence electrons. If you're talking about something like, say, sulfur, sulfur is atomic number 16, which means that it has 16 protons. And it has, let's see. Okay. So if you're looking for the effective nuclear charge for a valence electron of sulfur, let's actually work this out. That's going to be Z, which is 16, minus the number of core electrons, which is going to be the total number of electrons, which is 16. And sulfur is in group 6A, so it has 6 valence electrons. So that's going to be 16 minus 6 for the number of core electrons. 16 minus 6 is 10, and 16 minus 10 is 6. So the effective nuclear charge on a valence electron in sulfur would be 6. And that's how you can do it for other elements as well. And you can actually explain the changes in size of atoms moving left to right within a period by looking at the effective nuclear charge. As you're moving left to right across a period, say like this, the number of core electrons is remaining the same. Because remember, we can use noble gas abbreviations for the electron configurations of elements. The noble gas abbreviation represents the core electrons, because we're assuming if it's a ground state atom, all of the core electron positions must be filled in. And so the number of core electrons actually remains the same as you're going across the periodic table. And so the shielding on the valence electrons remains the same as you go across any given period in the periodic table. But the negative charge in the valence shell becomes more negative, and the positive charge in the nucleus becomes more positive for each step left to right. And so that results in a greater attraction, and they come closer together, making the atom smaller as you go left to right. The shielding of valence electrons by inner shell or core electrons also makes it easier to remove or add electrons to the valence shell as opposed to the core electrons. The core electrons are kind of hidden down there in the core of the atom, which is why we call them core electrons. And anytime you form an ion or form a bond with another atom, that's always going to involve valence electrons only, not core electrons. They stay the way they are. Okay, when you take an atom and turn it into an ion, its size usually changes, sometimes quite a bit. So the ionic radius is similar in concept to atomic radius, but basically it's just the distance, half the distance between the nucleus of two atoms that are involved in the bond when they happen to be ions. But the number for any given element will usually be quite different. Generally speaking, for any given element, the cation will be smaller than the parent atom, because remember, when the metals form cations, they do it by losing their entire valence shell. Magnesium has a +2 charge as an ion because it loses 2 electrons. It loses both of the s electrons in n equals 3, which is the entire valence shell. And now n equals 2 is the new valence shell for the ion Mg +2. And because of that, you're removing the entire valence shell. Well, of course, it gets smaller. So that makes sense. Anions are generally larger than the parent atom, and that's because of the extra repulsion of electrons in the valence shell. That is, electrons within the same shell will have a repulsion for each other because they're negatively charged. So if you're going to squeeze another electron into the same shell of an atom, they're going to want to get a little bit further apart. And if it's spherical, then that means it basically has to get bigger. So cations are generally smaller than the atom from which they're made, and anions are generally bigger than the atoms from which they're made. If you're talking about a given element and you're basically taking electrons away one by one, then the cation generally gets smaller as the charge gets bigger. So in other words, Fe +3 would be smaller than Fe +2. The size of an anion gets larger as the charge becomes more negative, which makes sense. I guess it gets larger when you take the first, or when you add the first additional electron. It's going to get even bigger if you add a second one, and even bigger if you add a third, because again, more and more and more repulsion of electrons in the valence shell. And if you've got cations with the same charge, then the trend is that the size of the ion will increase going down a group, and it's the same for anions, which makes sense because, again, you're adding a whole new shell of electrons as you go down a group. There are numerous ions and atoms that are what's called isoelectronic. And isoelectronic means that they have the same electron configuration. And we've actually already mentioned the concept, although I don't think I mentioned the name for it, when we pointed out that most elements form ions because, or at least most main group elements form ions in order to get to the same electron configuration as the nearest noble gas. Fluorine will gain 1 electron to become the fluoride ion because that gives it the same electron configuration as neon. Or in other words, the fluoride ion, F-, and neon are isoelectronic. And remember, that doesn't mean that the fluoride ion becomes neon. It only kind of looks like neon from the outside because it has the same electron configuration, but it still has the nucleus of fluorine. And since we define elements by how many protons they have, if you have 9 protons, you're fluorine, even if you have the same electron configuration as something else like neon. You're basically fluorine masquerading as neon, if you want to think of it like that. Okay, so things like, neon and fluoride ion. So you gain 1 electron. If fluorine gains 1 electron, it has the same electron configuration as neon. If oxygen gains 2 electrons, it has the same configuration as neon. So the oxide ion is also isoelectronic with fluoride and neon. The nitride ion gains 3 electrons, which makes it isoelectronic with neon also, but that means it's also isoelectronic with O-2 and F-, and so on and so on and so on. There are a bunch of them. You can even go for positive ions. For neon, Na+, Na+ has the same electron configuration as neon, because if Na with 11 electrons loses 1 electron, now it has 10, just like neon. So Na+ is isoelectronic with neon and fluoride and oxide and nitride. Magnesium +2 loses 2 electrons, which gives it 10 electrons, just like neon. So Mg+2 is isoelectronic with Na+ and neon and F- and O2- and N3-, and so on. So these are just some examples of species that are isoelectronic with each other. You can jump down and do the same kind of thing with argon. And you get argon being isoelectronic with Cl- and S2- and P3- and Si4-, and also K+, Ca2+, and Sc3+. It goes on and on and on. But these are basically, these are all isoelectronic with each other. And that's kind of important to know because, well, for one thing, being isoelectronic with one of the noble gases is what makes these ions stable and what causes them to form in the first place. But also, you can judge their relative sizes pretty easily if they're isoelectronic with each other. So if you've got two things, they don't necessarily have to be ions. You know, neon is isoelectronic with fluoride ion. But if you've got some isoelectronic atoms or ions and you want to know the trend in their sizes, the size is determined by their number of protons or their atomic number. The greater the atomic number, that is, the larger the number of protons, the smaller the radius will be. So again, it's a case where you're gaining something, but yet it gets smaller because of all that empty space within an atom. You've got the same number of electrons for anything that's isoelectronic. Throughout this entire series here, but the number of protons in the nucleus will be different. And so you've got the same negative charge around the nucleus, but you've got a positive charge in the nucleus that varies. And the bigger the positive charge in the nucleus, the closer it will draw the valence shell of electrons, and the smaller the ion or atom will be. Like the case of F- versus Ne. F- and Ne, like I mentioned before, have the same electron configuration. It's 1s2, 2s2, 2p6 for a total of 10 electrons. But fluorine still has only 9 protons in the nucleus, whereas neon has 10. So neon has more protons in the nucleus. It has a more positive nuclear charge, but yet it has the same negative charge around the nucleus as F- has. So neon will be smaller because plus 10 in the nucleus, but only minus 9 around the nucleus, or sorry, minus 10 around the nucleus, versus plus 9 in the nucleus and minus 10 around the nucleus. So plus 10 minus 10 has a stronger attraction than plus 9 minus 10 does. And so therefore, neon will actually be a little bit smaller than F-. All right. Okay, I think we're done with this segment of the video, but I'll be back in a moment with ionization energies.